Hi everyone, I'm Bingyang. In this video, I'm going to present our work of revisiting attention weights as explanations from an information theoretical perspective. This work is done by me, Suba, and Bingyang. Attention mechanism is first introduced for machine translation, and now is widely used in a variety of areas such as natural language processing, speech, and computer vision. The intuition behind the attention can be best explained by using human biological system. That is, when humans interpret a stuff, humans sometimes can selectively focus on some part of a stuff and ignoring the irrelevant part of it. Attention mechanisms do something similarly by assigning different weights to its input variables, and these weights can be interpreted as how much the model is attending to the input variables, and hence are used to explain the model's behavior. On the left of this slide, it shows an example with words with high attention values are highlighted as explanation to the model's prediction. However, if attention weights can be used as explanation is never formally evaluated. A more recent work called Attention is do this work by evaluates the faithfulness of using attention as explanation. This work shows some negative evidences that attention cannot be used as explanation. In this work, we show some promising results that attention can be used as explanation. We view the attention weights from an information theoretical perspective. Specifically, we focus on the attention mechanism in a typical encoder attention decoder scheme for solving NLP tasks, such as binary classification, question and answering, and natural language inference. We try to examine if attention weights can reflect the quality of information about the model's output that preserved in the attention input. To examine if the attention weights can reflect the quality of information that is preserved in each hidden state, we first rank the hidden states of each sample by their attention weights. Then we group the hidden states by their rank. Finally, we calculate the mutual information between the grouped hidden states with the model's output. By doing so, we can answer the question, if the hidden states of the highest attention scores preserve the largest amount of information about the output. To have a quantitative measure to reflect such consistency, we measure the Kendall-Tau correlation between the mutual information and attention weights. A higher Kendall correlation indicates more ordinarily associated between the attention weights and the mutual information. Our first results show that active and deep attention mechanism compared with the dot product attention are likely to be better at preserving information between the hidden states and the model's output. Additionally, we also found that the combination of BiLSTM encoder and active attention is better at preserving the correlation between the order list of mutual information and attention weights order. Based on the results of combination of BiLSTM encoder and active attention, we did an ablation study. We have two settings. Firstly, we fix the weights in encoder and decoder and train attention only. And secondly, we fix the attention weights and train the encoder and the decoder only. In this table, we found that for the fixed attention setting, lots of the setting, we get a decreased Kendall correlation. But for the fixed representation setting, we have an unchanged or even increased Kendall correlation, which indicate that the attention mechanism can actively learn to assign higher value to more informative hidden states. The third finding is that we find that when attention values are nearly the same, the rank order of attention values is not consistent with the rank order of the mutual information. We further examine this finding by using a Gumbel-Softmax, which are more likely to yield a more skewed attention score distribution. In this table, we show that there are 85 out of 99 sightings that can get an increased hand-eye correlation by using Gumbel